All right, here we go, kids. Lesson 7.1. We're estimating a population proportion. So in chapter 7, we're doing a lot of this estimating. Thought number 1. Number 2, why do we estimate? Well, because populations are hard to work with. Samples, super easy. But populations, not so much. Why? Because there's so many flipping people, so many flipping fish. It's hard to count them all. Therefore, what we're doing is we are making inferences from samples about populations. All right? So one of the key ideas is we're going to be kind of going back and forth between these two symbols. And one of them, this one, is a sample, whereas this guy is the population. And another word we're going to use is how confident are we of my difference between these two guys? Right? Okay, let's dive in. Number 1, point estimate. We're going to be using this phrase a lot. It just refers to the fact that something is estimating another one. And in this case, we're going from a statistic to a parameter. And in this unit, we're fixating ourselves on what we call a proportion. So P hat is a point estimator, wrong form of the word estimate, sorry, of P. And good news, we wouldn't be doing this if this wasn't an unbiased. Biased would give us slightly errors, right? One way or the other. Gallup, hopefully you are familiar with this term. These people here are pollsters. They gather information about our population. They publish that, they sell it, and people purchase that stuff. Not you and I, but typically people who are writing articles or some research, that kind of thing. A few years back, 43% of adults were on the Facebook, that which you no longer young people are part of. What portion of the U.S. Facebook has, what portion of the U.S. population has a Facebook page? Because we know that this proportion is an unbiased estimator, then with some confidence, and more words are coming your way about what does some mean. But basically we can say 0.43. Okay, would be a ballpark guess. This would be the easy way to do the section. Just whatever the sample is, bam. The actual population is the same. But we know that we might have made a mistake. There might be some little error creeping in because we didn't have a good sample. And so we're going to say, rather than just specifically, this is the value, we're going to say, with a certain level of confidence, here's the range of values I think it could be. All right? And that confidence interval is determined by the level of confidence. Every problem will tell you you have a 90% confidence level. If you have a confidence interval of 90%, that means alpha is 10%. Whereas if you're more exact, more precise, then obviously alpha goes down. This, you recall, is the tail. We're talking about these little tails out here. How much of that? What is the area? All right, moving on to our first problem then. We're just going to read this statement and interpret this statement. And the statement says, 1,487 people. Our confidence interval is from here to here. Here is the best way to read this information. We are 95% confident that the interval from 40.5 to 45.5 actually does contain the true value of P. So what that means is, if I can bop down to this one before to look at some bad examples of that interpretation, is that if I were to take many different samples, right? Boom, 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 right? And here's the one that I just did, right? that 95% of them would actually capture whatever P is. Once in a while, you're going to pick a sample, and it's a bad sample. It is off for whatever reason. All right? So we can't ever be 100% sure, but we can with a certain amount of level. Yeah. So here's some bad ways to interpret, again, this sentence. We have a 95% chance that the true value of P will fall between 40.5 and 45.5. All right? That's not technically what we're saying. P is a fixed value, and this isn't some random variable that's flopping over all the place. Okay, it's fixed. So again, the phrase is that if I were to take 95% more samples, yeah, that our particular sample, we're 95% certain that it's going to contain it. It's going to capture it. Here's another even worse way. We are 95% of the sample populations will be between that and that. This is based on a particular sample, right? Any one of these is just one particular one. All right. That, by the way, I think is the toughest thinking part of this whole unit, whole chapter. How do I interpret this? What does this mean? Critical values. What are these critical values? First of all, we'll be using this. I'll say find the critical values. So what does this mean? This means what is significant from what is non-significant. We label them with this little acronym Z. And this Z-score, you recall, divides the region into no confidence into two areas. So here we have the no confidence areas. Yeah. Notice together, alpha equals both of them together. The Z-score, there's the critical value that defines my critical region. And we have a normal standard distribution. So example number 1. Find a Z-score, alpha over 2, that's critical value for 95%. Here is the process that we do to find that. And they could give you any number here, and it's the same process, whether it's 94%, whether you want a 70% confidence level. All right, item number 1. Alpha is then 0.05. Alpha over 2 is 0.025. So this is what gives me these two values. Now, first of all, I do this one. That technically is giving me this region, yeah? And then I do this to be able to get this one. So this is the numbers I would look up in my chart. Remember that distribution chart? All right, so I'm going to flip there and look for 0.025. Doesn't really matter which one we look up. Both of them will contain it. All right. So you're pulling out your chart. I am looking under stats. There's my distribution charts. And again, I'm looking for 0.025. So I'm inside the interior here. Hopefully you're looking with me. I wish I could highlight this. I can't. But it is, okay, negative 1.9 on the left. Hopefully you can see the negative 1.9. And then slide all the way to the right, and you see 0.0250. Yeah? I think I can take a screenshot. Can I do that? All right. Sorry, the video broke off there. I gotta mend them together. Whatever. Here we go. So we were looking this up in the charts, and let me do this. Let me add a picture. Yay. Let me put it over here for now. And again, let's zoom into that area. So negative 1.90, negative 1.96. All right? But there's the value that we were looking for, 0.025. Now, it says negative. I'm not going to worry. This is showing me the left side. I want actually the right side positive. So, using table or technology, we know that the answer is either negative 1.96 or positive 1.96. If you were to look up the other value of negative 0.975, that's what's going to get the positive. They will typically say, give me the positive, right? So this is the z value we're going to enter into my machine. If you're to do the same problem again, only this time do it for 90% or 99%, these are the values you would get. Positive 1.645 or 2.575. So notice how extreme this is for 99% compared to 90%, which is a looser z-score. All right? Second of all, besides that, we need to know the reason we're getting that is so that we can find the margin of error. And the margin of error is how far off are we? What is the difference between our actual mean proportion and the sample proportion we get? What's the difference between those? Here is how we find that E for error. Don't be confused, this is not expected value from the last 2 chapters ago, okay? We're not calculating mu. We're calculating here the error. So again, as I cautioned, we'll need a z-score. We'll find that. Then we'll take our 2 proportions, our failure and success, multiplied divided by n. Take the square root of that result, multiply them together, bam, there's my error. Problem coming up in just a moment where we're using that. Requirements. When can I do this, Mr. Larson? Well, number 1, you must have a simple random sample. Number 2, you must be a binomial distribution. What does that mean? That means your data is discrete and you have a success and a fail probability. In this case, they're proportions. So the success proportion, the fail proportion. I got those turned around, didn't I? The P is success, Q is fail. Rewrite those in your notes, please. Number 2, you must, or number 3, you should check n times P and n times Q. Is that less, greater than, or equal to 5? If so, proceed. If not, do not go past go. Do not collect 200. Again, this is for calculating the error. Once you have the error, I can then take your proportion in the sample, subtract the error, take your proportion, add the error, voila, the actual proportion is captured by that. What confidence level? Again, depending on the problem. Okay, we'll typically, in this example that we're working through with 95%. Finally, we round our answers to 3 significant digits. So, before I proceed, big yeah, excuse me. Okay, we have to, we could possibly write this in 2 other ways. I could use the Plinus symbol, right? Notice how it's a combination of the plus and the minus. So the boundaries can be achieved by just writing it that way. Or I could write it in what we call the interval notation, and that's with parentheses. You've seen that hopefully in college algebra. If you haven't seen it, you'll see it for certain when you get into calculus. We write intervals in that notation. This is kind of like old school. This is new school, okay? It's cool to be new. All right, here we go. Gallup poll, same thing, 43% adults on Facebook. Find the margin of error using a 95%. List out the confidence interval. Big yawn. Now, we're going to answer a question. This is kind of a yes, no. Can we conclude that fewer than 50% of people have a page, on Facebook? This is, by the way, a very broad statement. Okay? Summarize. So the first thing you do in these problems is they're going to check. Have you done your requirements? Do you know that you're good, that you're able to use our formulas? This, you don't have to think about that, you bet. Bam. We're going to assume Gallup knows what they're doing. They're doing simple random. Is it discrete? Yes. Why? Because these are adults. They're whole people, not parts of people. Fixed trials? Yes. Independent trials. Does one trial affect the outcome of the next trial? Again, we're partly assuming that Gallup is doing a good job of making sure. Okay? So that's on faith that we know that. Number 2, what is the probability of success and failure? Well, in this case, 0.43 is my success. Fail is 0.57. So check, yes. Are we greater than or equal to 5 in both cases with NP and NQ? Again, you bet. Don't even need to multiply those out. You know that. Check, check. So you can go past go. You can collect 200 in this problem. Feel free to use the error. Yay, let's do it then. Here's error. So using the formula above, notice there's my z-score. We already found that. We have our probability, a proportion of successful people on the Facebook. And then we have 0.57 people not. Hopefully in your calculator that comes out to 0.025. I would recommend you practice doing that if you haven't done that at this point. Well, I take a breather. Okay, number 2. This is a coincidence that we got this 0.025, and we also had a 0.025 back here, where we did, what is my alpha over 2, okay? Those were not the same things. Those are two different things that ended up in the same position. So, quinkadink. So now I take, here is my proportion for the sample. I subtract the error. I take my proportion, I add the error, right? Together, that's going to form my interval of confidence. What confidence? 95% confidence level. Do I know that that less than 50% of Americans are on the Facebook? And the answer to that is yes. I do know that because this interval that I've got is, never wrote it out here, 0.0405, 0.455. Notice both of these values are below 50%. So yes. Okay. Number 4, again, how do I summarize this statement? What's the best way to read it? That's kind of, like I said, the toughest part of this problem, not doing the calculations, right? I know you can make little mistakes there. And reading this shouldn't be that difficult. But how do I understand it? 95% of similar polls, right? The percentage should differ by no more than 2.5 in either direction of the adults. So this error should work. It should capture the actual p-value. All right? Again, what's the connection here between the 95% and the 2.5? Well, notice that's 1.96. All right. So, just summarizing, when to analyze this, no inappropriate collection of data, no asking relatives, or sending out flyers and let people respond, right? We have to use some sort of simple random survey. They should give you the confidence level. In fact, you can't proceed if you don't know the confidence level. Sample size, yes and no. They will primarily give it to you. Some of the problems are going to have you actually come up with the sample size. But then if you know the sample size, then they're going to give you the error. More on that in just a moment. And then finally, quality. If you want good analysis, why, you got to have a good method and a good sample size. If those two things aren't present, then it doesn't really matter what you're doing, what type of math, you're left field. All right. So let me jump into like a little practice problem here. If you have collected some red M&Ms out of a bag, in fact, you emptied the whole bag onto a plate, and there the M&Ms are, and you've counted the number of red ones. They look like they're all red, Mr. Larson. Okay, we're assuming reality. Some of them will be red, right? So we end up by calculating a confidence interval, and what that means is that the next time I open a bag and I count the number of red M&Ms, I'm 95% confident that my interval, will be in this range. Okay? The true interval that I'm going to capture. In fact, the error should be the same regardless of the bag that you take. All right. Could I work backwards and figure out what my proportion of the sample and what my error was? This seems crazy. Like, how could you possibly do that? Well, it's pretty simple, actually. Because remember, if I take p hat plus the error, that should give me 0.37. And p hat minus the error should give me 0.12. So that means if I take these two numbers and find the average of them, right? What's the middle? Because in the middle will be, not p, this may or may not be in the middle, right? We know we've captured that. But this guy, p hat, has to be smack dab in the middle of my two values, because we added and subtracted the error to get there, right? All right, so add these up and divide by 2. So for example, in this case, it had to be 0.49 divided by 2. So 0.245. Bam. There's my p hat. And then divide the error. How far off is it? And then take 0.25, subtract 12. Right? What's the distance? That's 12 and a half. Hopefully if you add 0.12, 0.5, you would then get 37, and yes, we do. So there we go. We found the error and the p hat. So this formula here, I don't know if it's necessary here to write this down. This should be fairly obvious. To get the error, subtract, divide by 2. Or, on the other hand, you could find p hat by adding up the 2 and divide by 2. Either one of those will work. Once you find one of them, the other one's easy to calculate, but you just need to be able to grab one of them. Last thing, this is a long video. What sample size do I need to have a 95% confidence level? How many things do I need to have? Now initially, you got to get this formula down because you'll need it. As you write it, you should say to yourself, hold it. Didn't we have something with this? Because I remember doing p hat, q hat already, Mr. Larson. And yes, I'm going to flip back here quickly. You'll notice there's my p hat, q hat. In fact, there's all the elements. This means this equation and the equation I had was just like a resolve this equation except get n alone. So notice we're going to have to divide by that z score. At some point you're going to have to square things, and so that's why this formula here has those same things, only some of them are squared and they're flipped around because they were upstairs and downstairs kind of business. And then the last thing I wanted to say before I go here, before we do the last example, is that what if you don't know your proportion, your sample proportion? Well, here's an unknown status. I don't know my sample. Then the worst case scenario is that they were both 0.5. So they're going to replace the p hat q hat with 0.25. All right? So an example, if you want to assume, you want to figure out, okay, how many people do I need to go sample if I want to figure out what percentage of them are okay with buying things online. And by the way, I want to be 95% confident. Okay, number one. we look at a poll from a previous, and they say, oh, 80% of Americans make purchases online. Fine. Okay, so let's use the 0.8 as my p hat. So 0.8, 0.2 is my q hat. And then confidence level, I want to be 95% certain, so there's my z-score. And then I want to divide by my error, in this case, 3% of the error. All right, well that, hopefully when you calculate it out on your calculator, gets you 683. And again, make sure you do that. You don't get 683 exactly. We have to round, and hopefully you realize that we have to round up all the time, because you don't want to say 682.1. If you rounded that down, then you would be underestimating n, and that's bad. You never want to underestimate. Again, if you don't know the number of people, the proportions, then we would just take and replace those two proportions with 0.25. And the z-score and the error still stay the same. And I think, I'm not entirely sure, we get something like 1,064 or 1,065, I forget what the number was, doesn't really matter. But note that this is smaller than that, because in the previous example, we knew what the proportion was. Here we're assuming like a worst case scenario. The worst you're gonna need is 1,065. All right? There you go, good luck with estimating proportions in lesson 7.1. We found an error, we developed a confidence interval to determine